Okay, it's now, yep, it's now recording. Desktop. Okay. So, okay. Okay, so welcome to part two of Scala Camp. Unfortunately, that was quite a long and lengthy process in getting Zoom sorted, but yeah, let's begin. Okay, so do we need any kind of refreshers from what we looked at last time? So the last thing we looked at in the previous talk, we were looking at specifically, I'm just going to go back to where we were. We were looking at the desugaring of for notation into the equivalent of the flat map notation. So we were kind of like looking at this process in which we can take what Scala will do is we'll take a series of fors where it will take this was a flat map, this was a flat map, and then this was a map, and it would desugar it into this flat map, and this map. Did anyone have any big issues with understanding what was going on with that? Unfortunately, I'm sorry to the new people who have kind of come along. We would go over this, but that's in the previous video. Okay, so we've kind of come across this idea of there are certain data types that support a flat map, method, and it's kind of like useful for preventing the success of nesting, particularly in the case of optional where we want to access values that may or may not exist. Now, who here's used JavaScript? Yeah, everyone's used JavaScript. There's a method, it's called .then on promises. If we're all familiar with promises, you'll notice something quite interesting about how that .then method works, is that when you go some promise .then, you can return that function that you return can return one of two things. It can return some arbitrary value. In that case, it behaves like a map, or it can return a promise. In that case, it behaves like a flat map. You can't actually, JavaScript does not allow you to put a promise inside of a promise. It will actually auto flatten it for you. Anytime you go try and return a promise from an async method, it's actually just going to flatten it down. So it will always return just a promise of some description. So we have this idea that, okay, despite it not being named flat map, the .then is effectively the flat map that we've been talking about this entire time. And so there's this idea, we're coming to the suspicion that promises might actually be monads or behave in ways that are similar to monads. Unfortunately, promises aren't monads, but we're going to see something interesting. We're going to make our own version of promise. And so the interesting thing about promise, we're not going to do it in an asynchronous version. We're going to do a synchronous version. And I will show you what it looks like at the end. So this is what it looks like at the end. We have this type called sync. And we have different methods that do some sort of I/O. We have a put string line, we have a get string line, reads from standard in, we have a write file, we have a read file, we have a delete file. And then what we want to do is we want to use the for notation that we've previously described that works with monads to kind of sequence these asynchronous, not asynchronous, but these synchronous operations in series. So we have a put string line, then we get some line from standard out, and then we put the line. Now, the really, really, really interesting part is when I actually run this program. Wait. Sorry. What will happen is nothing will happen. What is really interesting is we actually don't evaluate it. This whole thing here is of type sync. And we call this a lazy effect type, in that what we're actually doing is we're building up some sort of data structure with successive flat maps. And then to actually make it do things, we have to do something like this. We have to interpret the value that we've created at the end. And when we actually interpret the value at the end, if it actually hurries up and compiles, we will see that what it's going to do is it's going to ask for me to echo something. We're going to get the line, and then we're going to put the line. If we didn't have this line here, it would actually do nothing. We found some way to suspend and prevent actual effectful operations from happening and deferring its computation until we explicitly say unsafe interpret. And I'm about to show you how that works. Oh my God, please compile. Sorry, it's just taking its time down the bottom here. Okay, as you can see here, it's asking, please enter something to be echoed. I can go blah, 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 enter, and then it's going to echo it back. And so prior to that point, so this whole thing is a data structure that does IO operations for us. We're going to see how that works. So before we do that, we're going to look at a brief thing, which is how laziness works in Scala. So before I kind of glanced at, I looked at it in my first talk, but I didn't really get into it. So we have this notion of strict and lazy values. So for example, here is a strict value. We've assigned to this strict value something that produces side effects, in this case a log, and then the return value of this scope is the strict val return value. Then we have a lazy value. This value will not be, that what is inside this scope will not be computed unless we try and use lazy val. Lazy def is something in much the same way until we try and use lazy def, it won't actually, anything inside the scope will be computed. And then here's the really interesting part. Yeah. Okay. Strict parameters. So this is really interesting. If I try and provide one of these parameters, if I try and provide, for example, a lazy val to a strict parameter, in this case, it's just a normal parameter. It's a strict parameter. What it will do is it'll evaluate it. But a lazy parameter, if I try and provide one of these lazy values to one of these functions with that take a lazy parameter, unless the function itself actually uses it, it won't evaluate it. And so what I'm going to do is I'm going to show you how all of these work. In fact, so if you give a strict parameter to a strict value, it won't do anything. It will print. It will always. It would have always. Sorry. It has already evaluated the strict val, and this would have been printed. And you can see this over here. I will always be evaluated. However, if we provide a lazy value to a strict parameter, it will compute it because the function needs, it's strict. It actually evaluates the parameter to be applied to the function. If you have a lazy def and you apply it to a function that takes a strict parameter, once again, the parameter needs it, so it'll evaluate it. If you provide a strict value to a function that takes a lazy parameter, well, it's already been computed because it's strict, so it won't do anything. But if you provide a lazy value or lazy def to a function that takes a lazy parameter, it will do nothing because the function doesn't use it. As you can see here, you've got lazy, what the hell? Well, that wasn't doing that before, so fuck something up. Anyway, but now we're going to get to sync and how sync works. So sync is it's a class, and it takes one single parameter, which is called unsafe interpret, and that unsafe interpret is it's a function that takes no it's a function that takes no parameters and returns that value a, right? This is a wrapper around some sort of value, and we can say at any point in time later on, we can call this empty function with no parameters, and we can get that a out. And then we have this associated function called suspend, which uses this lazy kind of parameter. It says, if you give me some sort of parameter, I won't evaluate it. And what I will do is I will wrap it up in this function, and then I will put it inside of me. I've deferred your computation. You know, you can give me anything, and I won't force it to be evaluated. And as you can see down here, that's kind of what I'm doing here. I've created a safe get string line, right? And I suspend this operation, which is read line. So when I created this, when I call this function get string line, it won't read from standard in. It will suspend it. It will wrap it up in a function, and it will defer its evaluation. Yep. Yep. So, being the functional programmers we are, we don't like when things do stuff without values being associated with it. Like if something reads from standard in, or it fires logs or fires missiles, we want some value floating around that it's like, yeah, that either represents that operation, that represents that operation. For example, down here, we like this. This is ideologically, we think this is a good idea. We think it's good that we have a value that expresses this chain of computations. And ideologically, we think it's a good idea for the caller to be able to invoke this series of computations when we want to. We also ideologically think it's good for it to be a value because then we can manipulate the values in different ideas. That's what we mean by safe. We think it's a good idea. Unfortunately, that's quite ideological. Yeah.
Does that also mean that unsafe also interact with the real world?
Yes. By marking it unsafe, we're saying, yeah, actually now at this point in time, we don't have a value associated with it anymore. It's this returns unit. We don't have any value. It's going to go off and it's going to do shit, you know. So that's what we mean by unsafe. So here's the interesting bit. So because we've spoken about promises before, promises, they can be mapped over, they can also be flat mapped over. So how is that actually working? And now this is the really interesting bit. So to make a sinc a functor, what it works is we take some sinc and we have some function that we want to evaluate. And now this is going to be a bit mind-bending. We're going to defer the rest of this. For the next section, my words I'm going to say are deferred. We don't actually do what I'm about to say. We interpret the sinc to get the value out. We run the function. So now we have a new sinc that, when executed, executes some other sinc, runs a function. So we have a chain. We have some sinc and a function in between it, and then another sinc. But this doesn't run when you have a sinc. Does that make sense? Cool. We're suspending some sort of computation, which is this F. So if we do successive maps, so if we have some sort of sinc from, we read from standard in, and then we map add exclamation mark, add exclamation mark, add exclamation mark, we would have a sinc and then a function that adds a exclamation mark, and then we would have a sinc, and then a function that adds an exclamation mark, and then we would have a sinc. We've got these 3 layers. And so you can understand that when we run that, we invoke the function, and then when we unsuspend this, like the next thing in the chain gets interpreted, which then runs the next function, which then interprets the next function, which runs the next function, which interprets it. So when we interpret this stack of sincs, the entire chain of operations executes. Is that making sense? Cool. So what's flatmap doing? Oh, sorry, what's flatten doing? That's the thing we saw before. If we put a sinc inside a sinc, it's quite easy to flatten 2 sincs down. Flattening 2 sincs down. So we have a synchronous computation inside a synchronous computation that provides some sort of A. So we have a computation that's deferred that defers another computation, right? And we want it to just be one singular deferred computation. We want both to run at once. We don't want to get some other deferred computation. We're like, I said run, please run the value, you know? We don't want this nesting. It doesn't make sense. It's not useful for us. So we make a new sinc. We say, don't do this yet. And if I have this double wrapped sinc, I do an interpret and then another interpret. And that defers. We're saying we need to do this double interpretation when we want to evaluate it. As you can see, double interpretation when we want to evaluate it. And you can kind of see what's going on here is there's a common pattern to how we write a lot of these methods. For example, flatten, right? You can see here I've said unwrap, unwrap, rewrap. If we scroll back up to how our flatten on options was written, unwrap, unwrap, rewrap. If I had the implementation here, it's a bit scary, but later on, we're going to see that kind of pattern will keep happening. We'll have an unwrap, unwrap, rewrap for all our flatten methods. So in practice, so we've got our flatten method. We understand what's going on as we're doing this double interpretation to get rid of those extra layers. And so now when we actually look at the code that we've written, we can see that this flat map here If it was a map, it would create an extra layer, but we flatten down the computation. And here's now our next flap map. We would have double layer, and then we flatten down our computation. And then our final map, we don't have that double layering. It just works, quote unquote works. But you can kind of see that's kind of cool. Like, we now have a series of computation. It's a single value, right? We've got this value that we can sling around and give to other people, and it's not actually doing anything. And this is we like this. You know, this is good functional programming. And you can kind of see, as I was saying, this is what this kind of code desugars to from the for notation before. We have a put string line, and then we flat map it. We don't do anything with the value of the put string line because it didn't spit out anything. Then we go to do a get string line. And with that string, when it evaluates, this is the important part. We don't actually have the string at this point in time. We're creating we're providing a function that when we evaluate it, we want to take the string that is the result of the evaluation of get string line. And then we want to put string line. And then we take a map and we throw it into nothingness. Or we take the return value of put string line and do nothing with it. So we can kind of see that, yeah, we've deferred these computations, but we can still program against it in an imperative manner. And we can do that because we're building up a data structure that provides instructions that explain how it will actually work when we evaluate it. Cool. Any questions? This is heavy stuff. There's no shame in not understanding this right off the bat. It took me a long time to understand. Cool. Awesome. Let's keep going. So the really cool bit is we can now write kind of useful functions that, you know, here's like a kind of simple function. It takes a file name and another file name, and we'll copy the contents from to to. This will actually work, but I actually couldn't be bothered showing you that it's actually working in the background. It is writing data. And it will, it will read from this file, get some contents, and it'll write the file to the contents. As you can see down here, this won't actually do anything because we haven't called unsafe interpret. And it's only when we call unsafe interpret on this copy function that it will do anything. Cool. Making sense? Awesome. So, next thing, function composition. Function composition kind of makes sense, right? We've got two functions. This one's called showInt, takes an int and returns a string. And we have another function called isBigString, and it counts how many characters in that string. And if it's above or greater than or equal to 5, it says it's big. And so now we can make a new function called isBigNumber. And we have this kind of showInt, and then we compose isBigString. And now we can give it a number, and it will say whether it's a big number or not. Just counts the number of digits in it. Yeah. Yeah, and then is actually a function on just functions. Now, remember, can someone explain to me what the function signature of map was? Does anyone remember what that was? It was, yeah? Okay. Anyone? No one? Okay. It's some functor of A, some f of A. We take some f of A and we have a function from A to B, and then we have an f of B at the end, right? So classic example would be some sort of list, 1, 2, 3. There's our list of ints, our f of A, and we have some toString. Ooh. That's a function from int to string, and now we have a list of string, right? Now, what if I told you that and then could also be written as map? Now, functors I've spoken so far have been containers. Option contains 0 values or 1 value. List contains 0 or many values. Sync doesn't really contain values. It's kind of this like deferred container, right? when we have it, we don't actually have any sort of value inside of it. A sync of int, we get the int when we evaluate it. It doesn't really contain the int. Now, what the really trippy part is, I kind of want a whiteboard here, unfortunately, is that functions themselves are functors. Yeah, this is going to be a little trippy. So, what if this section here was the f in functor? What if the int arrow itself was the container of string? So we can say that this function contains strings, where the thing it contains is its return value, and that the functoriness part is the int. So what we can kind of say is the kind of functor part of any functor is that some part of its type never changes. And in this case, what we've done is we've taken some int arrow that contains string, and then we have a mapping function from string to Boolean. And now we have an int arrow of Boolean. F of A to B, F of B. Okay, that did it. Please, someone in this room must have been confused by that. No one could be nodding along to this. This normally fucks people up a bit. Okay, let's see. Let's look at the implementation of functor for functions. There we go. So this question mark, this is going to be fun to explain. So functions of any type to some other type. Here's that function there. It's a function r to some other a, right? And we have some other function from a to b, and then we get some r to b. Functor of a to b, functor of b. And so that's just simple, quote unquote, function composition. That's the functor, you know? We're actually able to map over other functions. So this intuition that you might have heard before about, oh, actually, no, functors are just containers. They're not. Some of them are containers, some are deferred computations, some are functions, which is kind of really interesting. And so here we can write the function that we had before is big M. We have show int, and we can map over the top of it with the is big string. We're allowed to do that. It's kind of funky. So functions are functors. Yeah, I'll show implicit hints. Show implicit hints. Now, if you look at how I've done this and then function, this is the actual inlined description of map, which is it's an unwrap, it's an apply, and then it's a rewrap. So map returns a new function that we get the old function, we apply the R, which is this one, to get our A out. And then we use our F, So we have our original FA, which is our functor of A. We use its R that we create the last function with. This is kind of trippy. To get the A, then we use the F to get the B out. We return the B. But you can see the pattern. It's an unapply, it's apply, and it's a rewrap. And if you go up here, we can see, shit, there we go. Where is it? Where is it? Oh no. Yep, here's the implementation on option. As you can see, it was an unwrap, apply, rewrap. And that's in much the same way, function one, unwrap, apply, rewrap. So there's a pattern in much the same, for every time we do a map, there's a pattern to how we do our implementations of our map functions. Here we go, we have unwrap, apply, rewrap. perfect. Ta-da. So if we, cool. Sorry, it's kind of hard to code up here. Cool. So yeah, implicit hints, functor extension. This is the functor extension that provides the map function that wraps itself around functions. And then here's the functor1 functor instance that we have declared here and then instantiated here as an implicit definition. And the important part is this implicit definition works for any function of R, from R, right? For any function that goes from R to some other value, we have some functor instance for it. Cool. Yeah.
So in this case, am I right to understand that R is int because you redeclare it in the left-hand side?
Yeah, R in this case is int. And the functor aspect is int arrow, which is kind of interesting.
So in this case, would it not compile if the left-hand side is not provided?
Correct.
Because there's no evidence.
There's no evidence. Yeah. Okie dokie. So if functor is, if functions are functors, are they also monads? What if, rather than some R to an A, and we have some function from A to B, we have R to A to R of B? Because that would be how our FATMAP function looks like, right? Remember what the FATMAP function is. It was a monad of A to a monad of B returns a monad of B. There's nothing stopping us from writing that function. Like, it's just threading R's around and making sure that the right parameters go in certain spots, you know? And let's do it. We can do it. We follow the types. We'll let the compiler tell us when our types are wrong. And so here I am. I just hacked it together. Bam, wrote monad for functions. Kind of, I wouldn't say simple, but it yells at you if you do it incorrectly, you know? And so FATMAP, quite happily, we have some R to an A, and we have some F that takes an R, returns an R to a B, and returns an R to a B. You don't really actually need to understand this. That's kind of a fucked type signature, if I do say so myself. And the implementation is a lot of kind of like making sure that certain values are threaded into each other in a certain way. The kind of critical part is that the actual core implementation of how the FATMAP works is in much the same way. We have an unapply, we have an apply, we have an unwrap and a rewrap. That's exactly what we saw in the kind of sync implementation. Because here's the unwrap, here's the apply, here's the unwrap again, and then you finally got the rewrap for the final type. Now, I'm kind of getting to the point that I don't want to show you the implementations of how we write our monads. Because critically, we need to start remembering that monad is an abstraction. It is an interface, that we don't need to understand how this works. So if you're not understanding how this FATMAP works, good. All you need to know is how to use it. Now, what is really kind of interesting is, while this map kind of intuitively works in the much the same way as function composition, how FATMAP works is far less intuitive. But we can actually observe, the effect of how it's used. Now, I'm about to scroll down, and I'm going to show you how it actually works. And I want someone to explain what it's actually doing. If I can, I'm gonna actually write out what's going to happen. Oh, yeah, here it is down here. That's what it does. Can anyone explain to me? So wait, I'll just say, here you have your functions on your right-hand side. And then inside here, you've got your flat maps, you have another flat map, and you have your final map. So we're doing monad-y stuff with this do notation, where the thing on the right-hand side is the monad. We saw that in the previous examples with our for notation. In part one, we had on the right-hand side of this for notation, we have list, which is a monad. We had option, which is a monad. Today, we also had sync on the right-hand side, which is also a monad. And here we have functions, which are also monads. We have monads on the right-hand sides of our arrows on for notation. So intuitively, what is this doing? If you look at the final result type of running this do transforms, what it's doing is this do transforms, it's a monad of int arrow. So it's a function that takes an int and it returns this big fat tuple of 3 different values. And you can kind of see if the monad, because it's a monad of int I'm going to call it monad from int. On all the right-hand sides, we have monads from int. But they all return different types. This one returns an int. So we have a monad of int. Here we have a monad of string. Here we have a monad of Boolean. And so we have our monad of int, and then we flat map to take an int, which then we return a monad of string that takes a function from string that returns a monad of Boolean, flat mapped, that takes, mapped with a function that returns Boolean, that finally returns a big fat tuple. And as you can see, there's the desugaring of that function right there. As you can see, int function, flat map, add 1, returns another function, flat map, returns another function, and then a final map that returns a tuple. And then that final return value is that tuple. And so the final return value of this big fat chain of flat maps is a function from int to a tuple. And so what it's doing through this entire process is it's threading this value, this int, into every single one of these parameters. And as you can see, we've fed in 0 here, so we add 1 to it. We've fed in 0, so we turn it into a string. We've fed in 0, and we find that it's even.
Is it true, if I read this correctly, this is synchronous operation, right? So it's going to add 1.
Yeah.
And then do string.
Yeah. It's gonna do all these operations in sequence. So you don't really need to know how this works. In fact, you don't really need to know how this desugars. You just kind of have to know that if you put a function on the right-hand side and you make sure that all the functions on the right-hand side of this arrow take the same parameter, you get a big fat function that also takes that parameter. And it allows you to return a big set of other parameters at the end if you want. We give this a special name. It's called the reader monad because it reads from this value. And it's just made out of simple functions that we've composed together with flat maps. Making sense? Cool. Okay. Any questions? 5 minute drink break. Cool. All right. This next bit's fun. I need water. Good.
I know how you to make sure people get this, you have to give the talks twice.
Hmm.
Yeah, first time, scare them.
Yeah.
Second time, it's everything that was supposed to be there
Starts to click. Okay. Sorry about that. Yeah. You're the Haskell guy, right? Haskell guy?
Yeah.
Cool. How's it going?
Pretty
Syntactically, you're a bit like.
yeah.
I was like, I knew Haskell before I started Scala, so I was like, the first time I did it. So yeah, like you can't just. It's very hard to add type classes to things. It's hard to like compose things together as well. Like you have to add all these extension methods. Oh, hell yeah. Okay, let's keep going. So, section 2. Now this, I want everyone to remember the thing I kind of said, which was monad is an abstraction. Because I'm about to show you a type. I'm not going to show you how it works internally. Everything else before, if you want to actually know how it works internally, you're going to have to go to the source code and you have to look at it yourself. But I'm going to show you this type. It's called state. And I'm going to say it supports the two abstractions we've already spoken about so far. It's a functor and it's also a monad. So we know that we can map on it. We know that we can flat map on it. We know that we can use for notation. And then we know that what it's actually doing is it's building up a sequence of functions that at the end we can run in some sort of way. Why do we have this type? We functional programmers, we don't like variables. They're bad. They're the root of all evil. They're uncontrolled mutation. They are side effects. And as I said before, when we want to do side effects, when we want to print and fire missiles and stuff like that, we want some sort of value associated with that. Now, state is our way to do variables in a certain way that gives us values when we do the mutations to those kind of values. And I'm going to show you what it looks like when we run it. Ta-da! There's state. The monad part of state, it's a state of int. And then we have a big series of computations. Here we have a state of int, and then we have this modify function that adds 1 to whatever the state is. Then we have another function which is put. It puts some value 10 into the state. We have a modify that subtracts 2 from the state. And then finally, we get some sort of value from the state. We bind it to some parameter, well, function parameter in this, or variable in this case, whatever you want to call it, last, and then we yield some sort of string. As I said, the monad itself is state int. And because monads have take a type parameter, like list int, list string, option bool, this is a state int of string, f of a. This here, this state modify, is a state of unit. This put is a state of unit, where unit is a single zero value tuple. This is a state of unit. And state get is a state of S, where S is the same type of the state type, the int, right? So the return value of this state parameterization. So we have the F part is state S and the A part is S as well. So it's going to get the state out. Did that make sense? That was badly explained. Explain the bit that you didn't get of that. I can see it in everyone's faces. That was bad. Okay. I'm going to pretend it was good. But when we run it with some sort of initial value, 0. And what it's going to spit out, anyone know what the final value it's going to spit out? Yeah. In fact, it's actually going to spit out two values because that's how I've defined it. That's how I've written it. It takes some initial state S and it returns the final state, which is 8. And it's also going to return the A, where the A in this situation was the string, where the string was the thing I yielded. And so what it's going to say is it's going to say 8 and the final value is 8. That's what it's going to spit out at the end. So that's state. And state itself, it's a class, it's a wraparound a function from some initial S and returns some, yep. It might have been. From S, it returns a tuple, which is the final state of that state itself, and some return value. And we can kind of see what the gets, the puts, and the modifiers are built out of. Get takes the current state and returns as its A, that state. Put takes some new state and puts it in the state part. And modify takes some function and runs it against the state part. And then when we monadically compose those together, it's doing all the fancy stuff that threads the S around. Remember how we had the R and it was pushing all the R's all the way through? That's what it's doing with this S. It's getting the state out and pushing the state through the series of flat maps that we actually have built up. And so finally at the end, rather, we compose these little mini states that are just they're just functions from S's to tuples, and it's going to start threading and it's going to compose those together into a big chain that does some sort of stateful computation and also returns values. It's kind of funky. But we don't care. We just care that when we do this, it works. We just use for notation. It does the state stuff for us. Dope. Kind of readable, actually. Don't do it any other way, you know? And remember what I said. It's still a monad, it's still a functor. So we can run flat map against it. As you can see, we can put 5, we can get the value out if we wanted to, and then we can map over the final value, which is x plus 1. So what's this going to return? Anyone know? It returns a tuple, by the way, where on the left side of the tuple is the final state, where the right-hand side is the actual proper return value. No. The left value is 5. And the right value is 6. Because that's where we've put the state. Here we fetch the state into our value channel. So we've returned the value that we've recovered from the state. So now that's the A. And then we've mapped over that value, which gives us 6. So it's going to be 5, 6. Cool. It catches people. You've got to be very careful about that kind of stuff. But yeah, we can see it's both a monad and it's both a functor. But you know, you're probably going to use it like this. So, does that make sense? Cool. I'm going to give you a very brief glimpse of like the implementation, but you really don't have to know it. Ta-da! There it is. It's kind of spooky, but let's not worry about it. Cool. Does function composition always work? Maybe. Here's our get mother from way back. We have a function that takes a family member and it gets their mother. So it returns some optional family member, right? That their mother may or may not be alive, unfortunately. And so that's quite a simple implementation. It's just a function that takes a family member and fetches their mother. Easy. Cool. But does that work? No, that doesn't work. I'm trying to get the squiggly lines to pop up. The squiggly lines are not popping up. Come on. Nah, yuck. Ta-da. it expects an option to family member, right? So we wanted to write a get grandmother function, but we couldn't write a get grandmother function because the return value of get mother is an optional family member. We want to run the function again, but it's not letting us. It's saying we found a family member, but what is required is an option of family member. And you're like, oh, well, that kind of sucks, you know? And once again, here's another example of that not working. So we have this map function, get mother, it's going to return an option of family member. And so we have this get mother. So we have this grandmother, which is an option of family member. We're like, oh, okay, well, that's kind of annoying. I actually want that grandmother's age, but Scala is telling me that grandmother is optional because this get mother can return an optional family member. So we're kind of upset here. We need something that makes it work. And we're like, ah, shit, okay. Our functions that return monads don't really compose very well with each other. We can't go get mother, map get mother. We want something to make it compose nicely. What if we can do this? We have flat maps. You know, we're able to run one of these functions in a way that, you know, works quite nicely. So I'm going to show you what we build, and then I'm going to show you the implementation. Yeah, ugh, yuck. There we go. Get mother K. And so what we've done is we've built this thing called a Kleisli. We're going to get to what the hell a Kleisli is later on. I'm just checking the time. Cool. Still got 30 minutes. So a Kleisli is this, it's kind of this wrapper that makes our functions, when we compose them, behave a little different. And then when we have this function get mother K, and then we're quite free to sequence them. We can go get mother and then get mother and then get mother. And then we can finally get that age. And then we run it at the end. And so now our functions from family member to an option of int compose quite nicely. Yeah, look at that. That's dope. So let's actually see how it works. What's Kleisli? So a Kleisli, it's a wrapper. It's an actual class that you put a function of some description inside of it. And that function has to be of the form of some arbitrary A to a monad of B. So this get mother function is a candidate where the F itself is option and where A and B are both family members. So we're quite free to take this get mother function and cram it into a Kleisli. And now we have a function called and then on it, which is the composition that we saw before on functions. But it's a special composition because what it will do is rather than composing things with a map, it composes things with a flat map. So what it does is, given this A, it creates a function and it puts it in a new Kleisli. With that parameter to that new function A, it gets the inner value, the wrapped function, passes in the A, and flat maps the next function that we get here, K. So it's getting your one function, your A to F of B, and your next function, your B to F of C, and it's joining them together with a flat map. And then it wraps the whole thing up in a new Kleisli. We're going to see this pattern a few times, and it's a bit disgusting at first. You're like, ugh, yuck. And when I wrote this, honestly, I didn't really think about it much because anything I would write, the compiler would yell at me. I kind of just followed the types. I was like, what do I have? Oh, well, the A goes in the run, and then I have to flat map the next one, K run. Yeah, what's up? The little A comes from here. Oh my God, this Vim is really annoying me. Oh, sorry, this Slack, sorry. Yeah, the little A comes from the parameter, right? It's kind of, it's an interesting pattern, right? And it looks really, really weird at first because you're like, okay, I want to get the FB And how you start writing it is you start middle out. Silicon Valley reference. You start middle out, you get the run, and you want the FB. So you summon some sort of A, but you don't have that A, right? It's not available because it's a function parameter. So you make a function, and then you get that A and you pass it in. Now you have that f of b, then you're free to flat map that. Yeah, the run is a function. There it is, there's the function. Yeah, the argument, yeah, it is a self function. Cool, this is really quite hairy. Is everyone making sense of that? Cool. So, Kleisli, here's the map implementation. It's kind of disgusting. We have a Kleisli, and it's a function from A. Sorry, I lied. It's a function of from R to f of A. And we have this mapping function, A to B, R to A, f of A. And we have another function, A to B. And the final thing that we're returning is R to f of B. Right? Kleisli's being functions are also functors. But the functoriness is in here. There's the functor, the R to F. And then here's your mapping function A to B, and then there's your R to F, which is also the functor. And then there's the B in the final, the right-hand side. And so to make that work, we get your Kleisli, we run it to unwrap it, then we map it. And to map it, what we do is we have to do this map to access that, and then we do another map to map over the A, which gives us our B. That's really disgusting. Like, it's really hairy. These kind of implementations are really, really rough. But we're building them, they're type-directed implementations. I didn't cook this up. This is the only way I could have done it because the compiler didn't let me do it any other way. But it's also obviously a monad. I won't say obviously. It's a function. Why can't it also be a monad? So let's do the monad implementation. Yuck. Oh, that's a duplicative. Sorry. Here's the monad implementation. It's kind of really, really ugly. It's still got the rewrap, unwrap that we saw from before with the monad implementations. It's kind of, and the point is just, it's a double point. You know, the first point is to wrap it up in our F, where that F is our monad, whatever that may be. And then the point is to wrap it up in the function that we're actually returning. And then our flattened implementation, what it is, it's a run, and then it's a flat map, and then it's a run. Don't worry about that implementation. But what you need to understand is if you have two layers of Kleislis, at the end, you get a Kleisli. Cool. Now, that was the composition that we saw before that was really, really, really nice. You know, so we now have this function where the return type of the right-hand side is, that desugars to family member, Kleisli, family member option, family member, right? That's nice. We're free to use this function. We're free to compose these functions anymore. And because that is a functor, we can map over it. And if we wanted their age, we can just go map.age and we'll work. Cool. And then the thing we're mapping over now is this family member. If we ran it, we would see that the thing we were mapping over here was an option of family member. So this Kleisli is transforming the behavior of how our maps and our flat maps work. It's changing it. It's allowing us not to map over this, but to map over this. And specifically, that's exactly how the flat maps work as well. If I did not run that, when I would flat map over here, the thing I would be expected to return was a Kleisli. Whereas if I ran it, the thing I would be expected to return was an option of family member. But the behavior is changing a bit. This looks a bit, you know, what was the point? And we're gonna see the point in a second. We're gonna try and write some code, and we're gonna see why Kleisli helps. Oh, come on, Max, Jesus. Yeah. Ta-da! It's a fake router. Now, the kind of core funkiness of this is this thing at the end, which is a post handler. And this post handler takes a HTTP request and it optionally returns the HTTP response. And you can see kind of here that these posts return this function post. It takes a HTTP request and it returns an option of unit. If it's a post request, it's like, sweet, cool, that's a post request. And it says like, yeah, some, cool. Otherwise, it's like, no, I don't like that. Extract body takes the HTTP request. If it doesn't have a body, it gets the body. Otherwise, it gets upset at you and it doesn't have a body. It's none, right? Extract header. We have a map of headers. If the parameter doesn't, if the header doesn't exist, we don't return anything. But if it does, we return some, some header. Pass JWT token. We take some sort of string. We wrap that JWT token up. And then we have an interesting function here, which is extract JWT. And so it takes this extract header function, right? And our extract header function returns an option of string. But this pass JWT token takes a string. It doesn't take an option of string. If this was not a Kleisli, this would not compile. But because we have a Kleisli floating around, we're now able to sequence these computations. We can take something, we can take some option of string, and then we can, we can take a function that takes some option of string, takes some HTTP request, and then compose a function that takes whatever that string is and passes a JWT token out. Because we have this Kleisli around, it allows us to glue our shit together in a really, really nice way. And yeah, that kind of makes sense. Now this is the really, really cool bit. I want you to explain what's going on here. So I'm using the Kleisli as a monad. And here are some of the return values of this kind of function. I'm gonna give you some syntax highlighting. So you can see post handler. It's a Kleisli of option HTTP request to HTTP response, which when we run it, it's going to give us a HTTP request to an option HTTP response. And so each of these here, what it's doing is it's both doing the flat mapping for the option, because all of these functions return options, and it's also doing the flat mapping for the reader monad, because they're also functions, So we're passing in this HTTP request to both the post function. As you can see, it takes a HTTP request. The as admin function, it takes a HTTP request. Extract body, it takes a HTTP request. And it's also doing the optioniness of it. It returns an option. So if it doesn't exist, we have to return none. But we also have to you know, flat map those nuns. If it's a nun, we keep returning nuns. If it's a sum, we keep returning sums, you know? So we're able to do two monad actions at once, which is really, really kind of quite useful. Did that make sense? I actually explained this a lot better in my first lecture, I realized. Cool. And yeah, you can kind of see here, this post HTTP response, because we've got a body, it works. In this case, because we don't have authorization, we get a none. In this case, we have a GET request. It's not a POST request, but we do have authorization, so we get a none. So that's what's going on. And as you can see, we've taken our Kleisli, we've composed a Kleisli with another Kleisli, and we've used run to turn this into a raw function rather than a wrapped Kleisli. Cool.
Am I right to understand that if any of those check fails, it's also going to short circuit this?
Yeah, the whole thing will short circuit. If that's GET, oh, sorry, yeah.
Every other thing will not get computed.
Yeah, nothing else will get evaluated. So yeah, we're able to use this to do extra computation for us. So remember how I said it was a transformer? This is the reader T you might have heard about. Kleisli is the same as reader T. So what we can do is we can use reader T and we can wrap it over some function that returns a monad. And now we can do both at once. It gives it additional behavior. And it makes the type sign up in a really nice way. Cool. Here's another example that might help things sink in a bit. Here's a function. Now, rather than being option, we have sync. That's the monad. That's the monad we're transforming in this situation. So what we've got is this is a function that we have an A. If we go back up to Kleisli, there's Kleisli, 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 Kleisli. It's an A to an F of B. In this case, our A is string and our F is sync and our B is unit. Here's our string, F, string, string, F, unit. And we're able to create, when we run that friendly echo, run max. Oh, when we run it, we unwrap the Kleisli that we've sequenced together with fat maps. Yeah. And we'll see that that is, holy shit, come on. Sorry, I don't use this keyboard often. It's a string to a sync of unit. And so when we provide that string, which is max, we get a sync of unit back, and then we can unsafe and interpret because it's a sync. So we're doing two monads at once. We're doing the reader monad and we're doing the sync monad. And each of these flat maps is handling both of those monads at once. It's flattening the successive layers of functions to push through this string, and it's flattening the deferred computations, which is this sync here. Now, the reason I personally wouldn't explain this by the second Scala lecture, but in the Mega Man code base, Kleisli is a pretty core abstraction to a lot of the code that we have written. It's referenced pretty much in every file. And you'll look at this Kleisli and you'll be thinking, what the hell is this? This is what Kleisli is doing. And specifically in the Mega Man code base, our main, its type result is a Kleisli of HTTP of either future. HTTP request to A, right? So all our controllers are returning this type. And so the controllers themselves return a function that receives a HTTP request and returns some asynchronous computation that can fail, but returns an A. That is the return type of our controllers. That's why I'm introducing Kleisli. Unfortunately, this is the way it is. It's 0 to 100 a bit, but that's the case. So this is the implementation of Kleisli. Did that make sense? Hopefully it did. Any questions? We still have 20 minutes. Ideally, I will take questions explaining more things. Everyone understanding? Otherwise, we will have to go to semigroups and monoids. You'll force me to. Yes.
What do you think is the primary benefit of having Kleisli?
I wouldn't say there's a benefit. I feel like it's like a necessity to get things done. Like, yeah, like the common example I've seen Kleisli's used for is like, yeah, you have some R to F of A and you want to map over the A, you wrap it in a Kleisli, right? Because that's exactly how, you know, our map implementation works. You've got your Kleisli, you give it an A of F of B in this case, and now your map transforms that A to a B. It's not touching the F. The F is the same. We don't have to touch the option if we put the family member to the family member option of family member. If we want, we can get the age out without any double mapping.
Because I think it's super interesting to know that, you know, because HTTP request is in the left side.
Yeah.
And it's because it's a reader monad, it's going to be available in the tree.
Yeah.
And therefore you can inject various behaviors like tracing, you can inject stats T into it. And in the future, if you want to inject some other behaviors, like middlewares.
Yeah. So what Mitch is kind of bringing up for those who don't know is that a lot of, we're going to get to this probably by talk 3, but there's different types of monad transformers. So we had this, if you looked at reader T, there's an option T, there's an either T, there's a list T, there's a sync T. There's all these different T's, right? And they transform how monads, when they're flat mapped, work. And you'll see in a lot of applications, there'll be multiple layers of these transformers, so that every flat map is doing other flat maps as well. You'll have 4 flat maps going on at once. So option deals with unavailability of values. If one value is unavailable, then the whole computation returns none. And we saw that back with a family member. If you don't have a father, then successive calls to map to get an age won't happen. It'll just be none. And reader T dealt with successive calls to thread some sort of value in. If you need a failing asynchronous config providing function, you would use a stack of 3 separate monad transformers. Cool. Next, yeah.
I have 2 questions. First one is which plugin are you using as a projector?
It's just Kind Projector, yeah.
The second question is, why did you create your own type for either future instead of
either future is actually a monad transformer itself. It's a either T over future. But in the Mega Man code base specifically, it is that's what it's alias to. So yeah. Okay. Anyone done group theory in like grade 12 or something? No? Was that just my school? Okay. Oh, cool. Okay. Now this is going to get a lot simpler, which is great. Yeah, we have time. No, maybe we don't, but let's get to it. Semigroups. So semigroups. Some A that is a semigroup is you can smush the 2 semigroup things together. The common example is addition. You know, you have 1, it's a semigroup. Oh, it's a member of a semigroup. 2, it's a member of a semigroup. Smush them together. You have 3. It's also a member of a semigroup. Cool. That's kind of nice. And then we have this like special little diamond, which represents operations between things that are semigroups, right? That's the interface for dealing with them. So back again, syntax. We have some value that for some arbitrary m, we can have a class that wraps itself around it. We define some new binary operation between that M and some other M. And if we have evidence that we have an implicit instance of a semigroup, we can use that instance's definition to smush here and there together. Cool. And here's some instances for some pretty commonly used types. Int is addition. For lists, it's list concatenation. For maps, we have a special one where if there's a shared value, we're going to use the right-hand side. If we have like two maps, we just merge them normally, but yeah, the right value takes precedence because we merge if they have a key collision of some description. That makes sense. And then we can, if we wanted to, do I do it down here? Yeah, oh, shit. Oh, yeah, let's talk about monoid next. And so monoid is an extension of semigroup, as you can see, extends semigroup. Everything that is a monoid is also a semigroup, and they have some extra type of value, which is the identity, which we're going to call mempty for reasons. But that identity, if you try and use the semigroup operation against another semigroup with mempty, nothing should happen. So if you try and add an empty list to another list, nothing happens. It's the same list. You try and add 0 to a number, you add it, nothing happens. You try and add an empty list. If you try and merge an empty map with another map, nothing happens. That makes sense. And here is, we're gonna introduce two little functions that we're gonna talk about a little bit later. First of all is mconcat. And so what it does is, if you have a list of those monoids, what we're gonna do is we're gonna smush them all together. So if you have some list 1, 2, 3, and you call mconcat, it's gonna be 6. And then we have another function called mconcat_map, which is kind of simple. It's a map, and it's an mconcat. This is a weird function to tell you about, but we're going to get to that in a second. Ta-da! Here's some examples of us using monoids. Ta-da! Kind of simple. Yeah, mostly simple. There we are. We've got 1, diamond 2, 3, mconcat on a list, 6, merged. I don't know why my voice is doing this, by the way. List of maps, also merged. And we can kind of see what's going on with our implicit parameterization. We can see that that's going to be semigroup syntax, and all the instances for the appropriate classes are also being threaded in. Give me a second. Yeah, there we are. Lots of instances. Yeah, so that's kind of cool. And so we've kind of built this really useful type class, this kind of interface that's really good at smushing things together. And so I have 10 minutes. So we're gonna look at something, which is we're going to build what is do we want to do that? Yeah, let's do this. This is, who's written code like this? Anyone written code like this? It's like a little interpreter, What we've done is we built data. We make these little case classes, right? And then what we do is we wrap them up in lists. And then what we do is once we've wrapped those pieces of data up in lists, we call this a smart constructor. It takes some set of parameters, puts it in some sort of little case class, some little struct of some description, puts it in a list. And then what we do is we call these functions, we glue them all together into a program of some description. And this is like a poor man's dependency injection. You know, we can make two sets of interpreters that takes these things, these pieces of data, and interpret them. So we have one in production that actually goes off and like writes things, like writes files, it reads files, it deletes files. And then we have a test interpreter that what it will do is it will write things to maps. Read files doesn't do anything. Delete file, what it will do is it will go to the map and it will null out that specific field. Has anyone done this? Like, I think I've done this a few times, you know, when like testing, you've done it. It's all right. It works, you know. And we can use this mconcat map function to run it. You know, we have a program. Our program's a list of file operations. And then the mapping function is this interpreter, which takes some file operation and interprets it to a list, which a list is a monoid, right? This test interpreter takes a file operation, returns a map. And so both of these, this will actually execute and this will return the final result of the program, where the final result of the program, I think it's just going to be, yeah, it's going to be A, B, B. And that's what it's going to spit out here. It's going to be like map, A, etc. You know, that's what it's going to spit out, right? The kind of interesting part is, one, we've done something that we good functional programmers should not have done, which was when we ran this, we did side effects, right? This prod interpreter went off and it did an unsafe write file. It didn't return a sync. We should have returned a sync, but we didn't. We went off and did spooky things to the file system. And we returned this list of unit, which is a sin, you know. That should have been a sync, you know. We should have somehow returned, and particularly this read file. We don't even read the file. We just log, you know. We should have returned the value somehow. And the next thing is, like, we can't write this append file function. We want to, but we can't. We have this series of operations. We can build a useful program out of it, but the program can't have computations that depend on previous ones. We have this read file, we get the old contents, this is a append file, we delete the file, and then we write the new file with the old contents with the new contents added at the end. But that's not correct. Our old contents, it's a list of operations. It's not the actual file contents. We've fucked up, you know. It doesn't actually read from the file. It's just a list of operations, you know. This isn't correct. In some examples, you could have done something that worked, but unfortunately, this example doesn't work. But you know, there's a glimpse of something kind of nice here. The fact that we can have some sort of program that's data. You know, we like that as functional programs. We like having programs that are data, but we just don't like our interpreters committing side effects, and we don't like the fact that the data that expresses subcomputations can't be depended on. So the next talk, I'm going to show you a way to make this example work. And I'm going to tell you about what its name is, but I'm not going to show you what it is. So first of all, I want you to consider something really interesting. A linked list, it's a recursive data structure where the linked list is either it's a value and a pointer to the rest of the linked list, or it's just the end of the linked list. And so here we can make a linked list, and we can map over it. We can have a function that says, given a link and a head and a tail, map over the head and then map again over the tail. But if you reach the end of the list, stop doing anything. So we will recursively traverse through this linked list, running functions against each value inside of that linked list to kind of transform every value. This list is the free monoid. Because what we can do is we can have values that are not initially monoids. So we have this structure, this linked list, this structure that embeds things that are not monoids. We can convert those things that are not monoids to monoids, and then we can flatten them down. And we say it's free because we can defer the monoidness to later on. The list data structure we know is a monoid. We put things in it that are not themselves monoids. And then we have some function that takes those not monoids to monoids, and then we flatten them down. Because the list, this is a sequence of operations. This is one thing, two. This is, the list encodes that sequence. You've got thing, then thing, then thing. Like we can keep doing this, right? 3, 4, right? And we can quite easily replace these with commas and we would have a list. It's a sequence of operations. Monoids are sequences of operations that combine down to something, and lists contain sequences of values of some description. So that's the free monoid. Next time I will show you the free monad. And I'm going to leave you on that. Thank you very much.